Okay, so go ahead, Ivash and Diganta, start the tutorial on self-supervision, and yeah, that's it. Go for it.
Thank you for the introduction. I think I'm not sure if everyone wants to do the collab first or do the questions alongside. Um, I suppose we can start with the collab notebook, which Diganta would take over, and then if you have questions in the meantime while he's explaining or something, feel free to put in the chat. Then, yeah, we can start with the collab probably.
Yep, sure. Right, let me share my screen first. I guess we can see my screen.
Yeah.
Yeah, you can see.
Okay, let me just try to share this. All right, cool. Yeah, hi everyone, I'm Diganta. Just a quick intro. I'm a research master's at Mila in Montreal. I primarily work on sparsity and theoretical deep learning. Considering this is a workshop on medical deep learning, I've previously tried hands-on segmenting intraoral periapical abscess radiographs using segmentation models. So I thought it would be nice to experience this workshop with everyone. So yeah, that's pretty much about me. But today, as we are in the week of the self-supervision, me and Ivakshi thought of constructing a collab, which primarily is about a very fundamental approach, at least in visual self-supervision based model training, which is called as MoCo or momentum contrast. Uh, if people are already familiar with it, that is great. I assume from the last week when we went over the SimClear approach, this is a very competitive approach to SimClear. Just for disclaimer, this MoCo, which is in short of momentum contrast, has like 3 or 4 variants incremental to each other, but we'll be only going over the the first paper, the momentum contrast, the original paper that came out in CVPR 2019 by Fair, now Meta. Um, so I'll first give a brief introduction of what the paper does, why it is intuitive, why it works well, before going over the code. The assignment would be that we have um, put some comments in the collab notebook, where we have written your code goes here and a to do. So you are expected to fill in that line or the function, whatever that might be, um, and run it. Of course, all of the cells that you see below are executable on the collab provided GPU. So ideally, you should not have any difficulty. We also encourage you to try some different hyperparameters just to see how well it does, because self-supervised methods are a bit more sensitive to hyperparameter choices, especially choices in augmentation or batch size or learning rate optimizer. So we encourage you to try different approaches. Further, before I start, just so that we don't have any disruption, we try to gamify this tutorial a bit. So we have created a public 1DB dashboard, which I would encourage everyone to sign up for. If you guys don't have an account, it's free. I have put the link to to the website on the chat. So what basically it does is, if you once you have signed up, you would be able to log your experiment directly to a project dashboard. If you're familiar with TensorBoard, this is very similar to that, except that it is not explicitly local to your user. So you'll be able to log into this project, MedHack SSL, and underneath the project, you'll be able to see like live your test accuracy, how it is evolving, your learning rate, your loss, and your bug counter. And you can log it with your name so that it's easily identifiable who's running what, and you can compare the results against your peers so that it would be easier for you to build an intuition of how well these hyperparameters are doing. So yeah, if everyone, it's optional, but I would highly encourage you to do it. In deep learning research, reproducibility and experiment tracking is a very important component. So I would highly encourage to just sign up. It's free. So yeah. Okay, with that being said, I'll first, as I said, give an intro about the momentum contrast paper. So this is the paper, Momentum Contrast for Unsupervised Visual Representation Learning. This is a bit, I would say, archaic of a paper for self-supervised learning in the current timeline, but it still serves as one of the most foundational approaches out there for self-supervised learning on images, at least. I have seen this being extended to other modalities and domains like speech. I haven't seen explicitly this being used for medical imaging, but I'm fairly confident that it can be used to a successful degree in medical imaging problems as well. So going back, since we covered SimClear last time, this has a lot of similarities to that of SimClear. So we are dealing with a two-tower approach, just like SimClear. So we have an online encoder. So when I refer to encoder being online, that means that that encoder is allowed to be updated using gradient propagation. So the gradient only flows from the loss through this branch over here on the left. So this is the encoder that will be primarily updated with gradient descent. And then you have a correspondingly momentum encoder, which is what this paper is all about, as they say, momentum contrast. So this is offline, so that means that there is no gradient flow explicitly on this branch. So this is not updated directly from the loss. So what is the idea essentially of momentum encoder is that our primary encoder, when we do self-supervised learning, just to remind what the setup is, we do not have access to any labels. We only have samples. So we are expected to learn an encoder that can derive rich representation from the data, such that if we couple that encoder with a classifier or a predictor, either learnable or non-parametric, it does well on that task or a downstream task, right? So since we don't have access to labels and we do mini batch training, which is a noisy approximation of the full gradient descent, it's a bit hard to train these explicitly in a one tower model. So we usually have a two tower model such that we maximize the similarity between the two parallel encoders. So this will look very similar to that of SimClear or even a Siamese model. So the idea essentially is that our primary encoder is going to process a query sample or an encoded query, which is represented by Q. And a momentum encoder is going to process a dictionary of samples, which can be of the current mini batch. So as it has been written here, the dictionary is built as a queue with the current mini batch enqueued and the oldest mini batch dequeued, decoupling it from the mini batch size, right? So basically these are a set of samples and you get an encoded representation for each sample in that dictionary called k 0 to kn, and then you just do a contrastive approach between it. So you try to maximize the similarity between the queried representation encoding of the vector to its corresponding dictionary key encoded representation from the momentum encoder. And you will try to maximize the distance away from this X query sample to every other sample that doesn't match X queries, right? So that is the primary idea, but the main goal over here is coming from this momentum encoder. What that does essentially is it just updates. So anytime, so as I said, the left encoder is the primary encoder. So as you can see in this figure, the gradient arrow is only on the left encoder. So this is being primarily updated. So the way we update the momentum encoder is by simply taking a momentum approximation of the primary encoder update. So what we say is that after we have taken the gradient step on and updated the weights on this primary encoder, we are gonna compute the update for the momentum encoder by just simple linear approximation, linear interpolation step, where we say m, which is the momentum parameter, hyperparameter, times the update for theta k plus 1 minus m times theta q, which is the primary encoder. So what effectively this is doing is this momentum encoder is running at a lower rate than this primary encoder, which means that this is a smoother approximation of the weight updates that this encoder is taking. Going back to why it is important is because when we, so as they have written here, the momentum update in equation 2 makes theta k evolve more smoothly than theta q. So what that means is, because we are doing mini batch learning, which is noisy gradient descent, we don't want this primary encoder to take noisy steps consecutively, which might hamper or destabilize the learning process. So by making a smoother approximation of it in the form of a momentum encoder and encouraging both of them to be similar, we ensure that this encoder has a stable and smooth learning process. So that is the primary idea in this momentum contrast approach. And how it differs from previous approaches is that instead of this momentum encoder, previously what people have tried is to instead use a memory bank which contains the encoded representation of the dictionary keys either from a secondary encoder or a pre-trained encoder, and you just sample from that memory bank and minimize the contrastive loss. And the other approach is to literally use a disjoint secondary encoder, like a Siamese approach, where you allow gradient to flow through both the branches, and then you minimize in both directions, and you then merge them or use it as a full Siamese end-to-end network. So far, this is what the general intuition of Moco is. In terms of the loss, as I said, this builds on top of previous approaches like SimClear. So the loss function that is used is the info-NC loss, which, if I recall correctly, was discussed when we went over SimClear in our last week workshop. So this loss function should look familiar to everyone here. So if there's any questions about this, we can go over it. But I want to highlight a bit on the results and why this is such a important foundational method. So Okay. So what this paper shows is like significant improvement in results over a lot of previous approaches. They try out primarily with ResNet only architectures because this was at a time where vision transformers, I believe, hadn't come out, and also wasn't popular, at least in vision, the usage of transformers. So they show competitive performance against a lot of previous approaches in different model scaling capacity. As you can see this graph over here, where they're showing the sort of the scaling curve of how training a ResNet 50 with different parametric capacity um, is very, very helpful with the MoCo objective. And they also show the same significant result improvement when coupled with the problem of object detection on Pascal VOC against the end-to-end Siamese approach and the memory bank approach. So, and these improvements are pretty significant in the scale of object detection, at least in Pascal dataset. So, so yeah, that's pretty much what I want to cover about MoCo. There are a lot of experiments that this paper has gone over. They have also done key point detection, instance segmentation, dense pose estimation. So I highly recommend people to go over this paper because it's very versatile in its approach, and it works for a lot of different problem domains. So it would be helpful for people to try it out if they're working on something that has limited or no labels, even for medical imaging. So yeah, that is so far for the paper's intuition. But before I move ahead, I see there's some questions. Is it okay?
There are no questions as of now, but if anyone has any questions, can you please put them down in the chat, or even like if you want to unmute yourselves.
Yeah. All right, perfect. So we're sort of clear on what MoCo does. Now I'll give a brief introduction about the tutorial notebook. First, before we start, please make sure that you're making a copy of this notebook and putting it in your own Google Drive before you execute any cells below, so that there is no interruption of anyone else running this notebook as it is. But yeah, so this demo is for training MoCo on simple CIFAR10 dataset, which is a fairly standard small scale 10-way classification dataset consisting of 60,000 images, I believe. This should be pretty doable on a single GPU on Colab. So if people aren't familiar with Colab, before you start running anything, uh, click on runtime and click on change runtime type and just make sure that this is selected to a GPU. By default, it should be selected to a T4 GPU, but if you have Colab Pro, then you can maybe accelerate it by selecting a V100 or a A100 as you like. So right now this is a MoCo setup, which is this encoder coupled with the momentum encoder with the contrastive objective, but for a ResNet 18 only model. The reason we offer ResNet 18 primarily is because self-supervised methods in general aren't very compute friendly. Like they require a lot of data budget and also compute budget to reach a strong generalization performance. Just for the interest of time and the resources that we have on at least the free version of Colab, we stick with ResNet 18. But after the workshop, if you want to try out different architectures, you would be able to by just swapping out the ResNet 18 argument to ResNet 50 or any other model. Some notes. We have an option for asymmetric loss and a symmetric loss. I won't go into the details of what the differences between the two losses are. The symmetric loss is just following the SimClear and the Biol setup. if people aren't familiar with BEOL, it's fine. But if you have seen SimClear, they have a symmetric loss option which swaps the two crops and just computes an extra loss on top of the info in CE. So this, like as has been written, it behaves like 2x the epochs of the asymmetric counterpart. So to be consistent with that of the original Muko setup, the asymmetric loss is the default loss that will be used. There's an argument to switch on the symmetric loss, which actually gives performance benefits, as you can see from the benchmark. But it's not necessary for you to try it. It's just an option. If you want to play around with it, you can. There's another important part is the split batch ROM. This is a bit more of an engineering hack than I would say a fundamental or algorithmic approach, because the fact that these models or self-supervised models are generally trained on multi-GPU or multi-node settings. We usually have different ways to compute the batch statistics in the batch norm layer if they are being trained on different nodes or different devices. So because we are now going to train the same on a single GPU on Colab, we want to simulate the same setup that Moco has. So there is a class which is a modified version of the vanilla batch norm to essentially simulate the behavior of a batch norm when being trained on a 8 GPU setup. So you don't have to look at this section. This is just a disclaimer that we are not using the exact vanilla batch norm as it is. Finally, because the self-supervised approach is primarily monitored based on the train loss, because we don't have, ideally we don't have labels during training the self-supervised model. We provide a non-parametric evaluation using a KNN, where we are going to essentially, after every epoch of training with the Moco objective, this ResNet 18, we are going to plug in the KNN. I assume people are familiar with k-nearest neighbors. It's just a non-parametric approach to find the class assignment of a sample based on nearest neighbors based on whatever the k value is. So we're just going to do a linear classification on the CFAR 10 test set labels using a KNN after every epoch, which should be logged as you saw here to 1 dB in the form of test accuracy. All right, so as per task, as I said, you're supposed to fill in the code snippet where we have marked with an inline comment. Your code goes here with some to-dos and different hyperparameter settings that you're encouraged to try out, different learning rates, augmentation, batch size, and learning rate schedule. We want to emphasize on augmentations primarily because they have a very fundamental role to play in the case of self-supervised training. So we have encouraged you to try 2 different augmentations that I'll highlight when I go to that cell. And you can try learning rate and LR schedule on your own if you're familiar with some commonly used learning rate schedule. In this one, we follow the cosine TK, but if you want to try out some other scheduler like an inverse square root scheduler, then you are more than welcome to. I would not encourage a lot of people to try out different batch sizes, even though it is very important for self-supervised learning, because the batch size will clearly affect the runtime. So trying out different batch sizes might be very helpful as a general ablation study, but in the best interest of the time that we have, it might not be the best hyperparameter to play with. And as I said, yeah, please do try to sign up for 1db and log your settings on 1db. Okay, so I will just briefly go over the code cells below and explain what each code cell does sort of, and I'll highlight where you are expected to make changes or fill in your code snippet. And then we can sort of have an interactive session where you guys try it out yourselves, and we can see everyone's run on the dashboard. And if anyone has any issues or questions, then we'll answer or help that person out at that point of time. Okay, so the first code cell is just importing a bunch of packages. We'll be using standard PyTorch and Torch Vision for everything that we do here. that's pretty straightforward. So here is the first case where you'll be required to make any changes. So we have some arg parse, it's just a argument parser. This would have been more relevant if you were running this from a terminal instead, if it was a Python file. But instead, this is a Jupyter notebook on Colab, so it's not like we actually pass in the terminal arguments, but we have certain arguments that are important to play around with. So the first one being learning rate. So the default is set to what Mocha offers, 0.06. This is something that you are encouraged to play with because depending on the learning rate, your performance will vary quite a lot. We encourage everyone to reduce the epoch count to something like 10 or 20. The default is 200 to reproduce the results that are written in this table, but 200 will take a lot of time. Just to let you know, at least with my benchmarking on a single T4 GPU that Colab offers in the free version, a single epoch takes around 1.25 to 1.5 minute. So if you want to finish a full run, then it would be best if you can reduce it to 10 or 20 or like anywhere in between that in the time frame that we have. This is the schedule. This is the decay rate. So essentially this suggests that the learning rate will drop by 1/10 at 120th and 160th epoch, but this is not going to be used if the cosine learning rate is being used, because the cosine learning rate schedule has its own decay rate that it adaptively calculates every step, so we don't have to hard code the step at which we want to take a decay. This is only relevant if you're using a multi-step learning rate decay. So if you'll be using a cosine learning rate, which is what is used by default, then you don't have to worry about this. But if you will be changing, if you'll be switching this off and using a multi-rate decay schedule or any other schedule that has a requirement to define where you want the learning rate to drop, then you can provide like the default step number or the epoch number where you want it to drop by whichever amount. Then we have the batch size. Again, this is set to 512 by default, but you can try changing it, but yeah, not highly encouraged because it will change the runtime. The last thing is the weight decay. This is a bit important. We see a lot of self-supervised learning papers use weight decay by default to be at 5e-4, primarily with SGD optimizer. This is something that can play a role in how the update steps look like. So if you plan to use a different optimizer, not SGD, like you want to use Atom or AtomW for that case, then you can play around with different hyperparameters pertaining to those optimizer. But right now this is set default to for the SGD optimizer that we have. So those are the lines that you'll first be encouraged to play around with, the default values here, so that you can like just use different hyperparameters and not run the exact same thing. The last thing that in this cell block that you'll be encouraged to change is this line over here. So this is the run name, which is the name that reflects here, as you can see. So by default, it's MechMed Hack, which is the name of the workshop, but please change this to your full name or any other name that can be easily identifiable for you, so that we can compare, or you primarily can compare your run with your peers. So don't run it with the default, and it will be confusing to see who ran what. And yeah, you can change the epoch counter here as well. Primarily change it here, and if you're not using a cosine scheduler, then you can just make this false, and that should work. And as you can see right now, we by default have the symmetric loss function to be false, which is the SimClear loss, which we are not using. We are just using the vanilla Moco loss. So if you plan to try out later with the loss that was in SimClear, you can make this true. Okay, so if you do not plan to use 1db for logging for any reason, you can make this 0. One basically suggests that we'll be using 1db. If it is not 1, will not. So as you can see, this will only be executed if it is 1. When you run this, it will run a login key. So here it will require your API key. So once you go here to your account, you'll have an account like this. You can go to user settings, scroll down, and you'll find your API key here. So you can essentially copy this, and ideally it will put a text box here to put in your API key so that it logs into your account, so that it is identifiable who's running it. Okay, so moving on, we have the data loaders for the CIFAR10 dataset. This is the first important piece of the puzzle that you'll be tasked to change. So here, as we have written, apply, augmix, or cutout. So those are the two augmentation strategies that are very popular and very relevant to self-supervised learning. So we encourage you to try either of them. It's up to you which one you want to try, or both if you want to. Augmix is essentially a sort of a learnable randomized augmentation which composes different augmentations together, like jitter, horizontal flipping, color transform, depending on the severity factor and the max depth you are using. So both these augmentations are supported in default torchvision.transform, so they can be callable as transforms.augmix. You can search it in the documentation and see how it is used and the different hyperparameters that it incorporates. There is a corresponding paper for this, which if you are interested in, you can take a look. Similarly, you can find the cutout option as well. Cutout basically cuts random or learnable patches from within the image, depending on the patch size and the masking ratio that you have. So and if the need be, you can replace existing augmentations that are provided, which are horizontal flip, random resize crop, random grayscale. Do keep the random resize crop because we'll be using the same standard image size of 32 for the experiment. But you can replace like the horizontal flip or like color jitter to whatever augmentation you think would be beneficial for the process, right? So here we are creating the loaders. So we have the train loader, the memory loader, which is nothing but just the dictionary queue, and then the test loader that we'll be using with the KNN model. Okay, I'll stop for a while if there are any questions right now. Okay, none. All right, so considering there's none, I'll move ahead. So as I highlighted, we have this split batch norm class, which basically simulates the batch norm process, but in a multi-GPU setup when you're doing in a single GPU. You don't have to go over this. This, as I said, is a bit more engineering and research or algorithm. So you can just run it. You will have to run all the cells sequentially to make sure everything works. So do run it, but you're not like you're not forced to go over it in details. Okay, the next part is the primary part about the whole approach, which is the MoCo model itself and how MoCo operates. So you'll basically be able to see how the two encoders are created here, right? And here, as you can see, we make sure that the second encoder or the momentum encoder gradient is kept to be frozen or false, which essentially means that it's not going to be updated, or the gradient graph of it won't be calculated in the compute. So here is rather the important function that you'll have to write for yourself. So this function basically takes in the parameters that you have for um, the encoder Q and the encoder K from the previous step. And once you have done a single update on Q, you're going to apply the momentum update for K, right? So going back, as you can see, that is the formula. So the update step for the momentum encoder is nothing but the momentum coefficient times the update which replicates the Q setup for K, and then plus the 1 minus M, which is the momentum coefficient again, times the update step taken by the primary learnable encoder. Right? So that is what you're expected to fill here. It should be a couple of lines, if not 3 or 4 lines at max. So that's the logic that you'll have to follow to fill this here. You're not expected to return anything. You're just going to update the weights of K here, right? Then we don't have to look at DQ and NQ. This is just the queuing of the dictionary. This is for batch shuffling on a single GPU setup. And then we have the next important thing, which is the contrastive loss that is being used, which is the info NCE, as you saw from the paper. So the only thing that you'll have to change over here is to apply the temperature constant or coefficient in the loss terminology. So we encourage you to open the paper on the side, refer to it, and just see how or where the temperature coefficient is applied, because it's quite important. And you can plug that in over here, and everything else should be as it is. It should work. It should be just one line to add here. Then we have the standard forward pass, which does the full forward pass on the 2 towers and computes the contrastive loss as well. Okay, then we have the trainer loop. So this is the trainer loop that does the training of both like the update on the Q encoder, the online encoder, and then you take the momentum step on the offline encoder. You also have the learning rate scheduler adjustment based on whatever schedule you're using. As you see over here, if it is a cosine rate schedule, then it automatically assigns what learning rate would be in the next step. But if it is a stepwise schedule, then it will see based on the schedule list that you had passed. If it has reached that epoch number that you had specified, then it will reduce the learning rate by like 1/10. Okay, then we have a simple test function, which simply does a linear classification evaluation on the test set of CIFAR 10 using a standard k-nearest neighbor approach. So don't have to go over this. This is just for evaluation. And then primarily we have the training, the whole end-to-end training process. You are expected to define your own optimizer here. So it can be SGD, it can be Adam. You will obviously be using the default, the hyperparameters you have specified earlier, like the weight decay, the learning rate, or any other hyperparameter that is relevant to the particular optimizer that you use. For example, if you use Atom, then you'll have to specify the EMA coefficients. So this is something for you to play with. You can use for now any optimizer that is supported out of the box from Torch. So that can be directly plugged into this, right? And here is the main trainer loop where we do the training and the logging and also the test evaluation, as you can see. So yeah, and it is on verbose mode. So every epoch it's gonna print out the statistics here as well as log it onto the dashboard. And then after you have finished running, or even if you decide to stop running this by clicking this again, like after this is running, you can stop it by clicking the play button. Please do run this cell, because this essentially terminates the logging process to the dashboard. So if you do not click this cell or run this cell after you have either finished it or you have stopped the running, then it is still gonna keep syncing your next run to the same previous run. So it's gonna be a mismatch, right? So it's gonna assume that you're continuing your training rather than starting a new training run, right? So yeah, there are some disclaimers regarding to some hyperparameters and some references from where this code was sort of adapted. So that's pretty much it about the Collab notebook. I hope I was clear throughout. If there are any questions before we encourage everyone to start running it, I can answer them right now. If not, please feel free to open the notebook, make a copy of it by clicking file, going save a copy in Drive. It will open your own local copy, and then running it out. And I believe you have been shared the Google the Drive folder link where the solution notebook is also present. So if you feel something is unclear, you can always refer to it or ask us. We'll be present throughout this workshop session. So yeah, that's pretty much it. I don't think there are any questions, so I think we can start. I'm gonna stop sharing my screen for now.
Thanks, Diganta. It was awesome. It was very nice tutorial. Yeah, we'll take questions now, I guess. And remember that you can post questions on Discord as well. And the mentors will see it and respond at some point. It seems like there's really no question. So I can stop recording then.